Alright, hello CS11. This is lecture 20. For today, we'll be looking at more algorithms. So for today, we'll be looking at what we call divide and conquer, as well as sorting. So let's start first. So to motivate this lecture, let's look at the searching problem. So we've gone through this several times actually. The first time was when we were going over dictionaries. So let's start here. So you have a sequence of values. So some sequence of values. Let's say you're in Python and you have some random sequence of values here. And what you want to do is you are given some value and you want to find its corresponding index. So for example, if this is my sequence and I want to get the index of the number 1. So index of 1 should give me the value 2, since this is index 0, index 1, and index 2. So what I want is, if I'm given multiple values, I get the index of each of those values. So in this example here, this is the sequence, and these are the values you want to find. So yung 15, this is at index 2, yung 21, this is at index 4, and 10 is at index 0. The rest are not in the sequence, so you return none for them. So how do you solve this problem over here? So if you want to find the indices of a sequence and the values, then what you can just do here is for each return for value and values, you want the index of that value in the sequence. So let's say you have that, and you have an inner function here of some value. So for I in range length of the sequence, if sequence at I is equal to value, then return I. Simple as that. So if we have this and we now do find indices, let's use yung sequences here, 10, 20, 15, 17, 21, and 15, 14, 21, 55, 10. So if we use these two sequences, we get the values that we want here. So this is one solution to this problem over here. Another one is, well, we can use a dictionary. For each element here, each of the elements here, we map that to its corresponding index. So for example, we have 10 maps to 0, 20 maps to 1, 15 maps to 2, and so on. You would write this as something like, if you have a sequence, so this is your sequence, the dictionary is each element, then its corresponding index for I and X in enumerate in the sequence. Remember, enumerate, this gives you the elements as well as their corresponding indices. So if you do this, and I get D now, you'll see that 3 maps to 0, 2 maps to 1, and so on. So this is one way to solve this problem. But is there a faster way? So the answer here is no. There's probably not a faster way. Why is that the case? Well, the main reason is that if you want to find any element inside the sequence, in order to make sure that your search is actually correct, you will have to consider the entire sequence over here. So let's say, for example, I asked you, is the number 1 inside this sequence over here? You wouldn't know that unless you look at each element here and you see whether it's equal to 1 or not. So for any normal sequence over here, you would need to scan through the entire thing in order to find some specific element. Now what if the sequence was something else? So for example, if the sequence is sorted. So by sorted, what I mean by that is, let's say you have the same sequence, but you sort it. So now it's in increasing order. Now in order to actually find some element, you know that once you reach the number 3, for example, all of the next elements are going to be greater than 3. So if let's say you're finding for the number 2, you're not going to search anything beyond this 2 over here. Once you encounter this, you're gonna ignore the rest. So because of that, if you have a sorted sequence, you can actually do Thanos search or binary search. So let's say you have a sparser sequence, so 2, 20, 31, and let's say 35. So let's say you have this sequence over here, and you want to find the number 17. So in the sequence, what you're going to do first is check the middle of the sequence. So here, that middle element is 20. So you're going to compare 20 and 17. Since 20 is greater than 17, you know that all of these elements here are not going to be equal to 17, since this is a sorted sequence. So you can already ignore this half by looking at the middle element. So that's the idea here. So if it's equal, you've found what you want. Otherwise, you either go left or go right. So note that this only works in sorted sequences, since if this was any random sequence, you can't really say anything about the elements that come after or before a specific element, if it's arranged in random order. So yeah, it has to be sorted. Okay, so for example here, this is a slightly longer array, and you're also finding 17. So you start in the middle here. Since 11 is less than 17, you know that all of the elements here are going to be less than 17. So you ignore all of these. They're all grayed out now. So that leaves you with this part of the sequence. So you're going to do the same thing. Look at the middle, it's 19. 19 is greater than 17. So you ignore everything that comes after 19. So the rest of these are also grayed out. Here, you're going to look at the middle. Depending on how you define the middle, it's either this element here or this element. If you consider 13 the middle, then 13 is less than 17, so you ignore that. Everything else is already ignored. And finally, you reach the element that you want. So how do you implement an idea like this? So what we can do is, if this is the sequence, these are your queries. And for each of the values in your queries, you have a function call just for that specific value. And here you're assuming that the sequence that you're given is sorted, so that you can do this binary search over here. Okay, so this search function, how you would implement this, could look something like this. So what is happening here? So here, these are your inputs. And what you want to do here is you want to check whether this value is inside this sequence over here. So if the sequence is empty, then you have nothing to search for. So you're already going to return none over here. Otherwise, you're going to do what we mentioned a while ago. Look at the middle element. Then based on that middle element, if it's equal to the value, that's what you return. Or you return the index of the middle element. Otherwise, depending on whether it's less than or greater than, you make a recursive call. So if it's less than the middle, that means you have to search for the left half, like this case over here with 19. So you end up searching the left half. Otherwise, you search the right half. So this is how you could implement the search function. So for running time, if we think about what's happening over here, at each recursive call, the part of the sequence that we're searching for is cut in half. So that means that whenever you're making a query for each call over here, this is going to take log of the length of the sequence. So log 2 of whatever the length of the sequence is. So overall, if you have q queries, everything is going to take this amount of time. So q times log 2 of n. So if you have this function of q and n, and you look at, so from math import log 2, let's say q and n are both 10 raised to 6. If I do q times log 2 of n, This is around 20 million, and our estimate is 100 million operations per second. So this is still within our budget. This will run in roughly around 0.2 seconds using our estimates. So this is fast enough. On the other hand, if we did brute force, so for each query, we just literally searched through the entire list or sequence, that would instead be q times n. So n instead of log 2n, since you're searching through the entire sequence. And in this case, if it's O of qn, that 10 raised to 6 times 10 raised to 6, q times n, this is now 10 raised to 12. So 10 raised to 12 over 10 raised to 8, this is 100 million. This would take 10,000 seconds, which is a lot of time. So this is a lot slower. Okay, so you can try running this implementation. And what you should see is, if you run it like this, you'll see that if you try to run this implementation over here, this is actually pretty slow. So this, as well as this, all of this is actually going to run slowly. In fact, it runs as slow as the brute force solution. So why is that? Why does this Sano search solution run in O of qn time instead? Well, the reason for that is slicing. If we look carefully in the implementation here, whenever we're making a recursive call, we're slicing the original sequence. And remember, in the previous lecture, we said that slicing can be slow because it makes an entirely new copy. So if we look at what's happening here, because of all of the slicing that's happening, you can think of it as whenever we're making a recursive call, we're also inducing the cost, or we're having a cost of copying this sequence over here. So aside from all of the other operations that go on inside the actual function, in this recursive call here, we're already making quite an expensive operation, which is why, all in all, this whole thing is actually pretty slow. It becomes O of n per query. So how do we fix that? Well, if the main problem we're encountering is with the slicing, as we went over in some of the previous lectures, the main way to go around that is by using index-based recursion. So in your recursion, you also include the indices that you want to work with. So index-based recursion, what would that look like? So here, we have the same find indices function, but yung search function natin, aside from sequence, we also have some other parameters over here. So value is the value we want to search for, and now we have some additional parameters here. So these are now the left and right ends of the part of the sequence that you're searching. So originally, you're searching through the entire sequence, and as you go through the middle element, that search space, or the range of indices that you're looking at, becomes smaller. So based on m, you either now search for I to m minus 1, or the left half, if the value is less than the mth element, the middle element. And otherwise, if the value that you're searching for is greater than the middle element, then that means you have to search the right half, or m plus 1 until j. So this is now the index-based version of the search function. So if we try this again, or if you tried using this and running the code from a while ago, this one, you'll see that, or you should see that, it becomes a lot faster. So again, if you see that in a recursive function, you are copying the sequence, you might want to make the function, or turn the function into a index-based function instead, or use index-based recursion instead. Okay? But all in all, the idea here is if you have a sorted sequence, you can also do Sano search on that sequence. The idea is the same. Just like with the egg dropping example, we divide some range in half at each step. here, that range that we're considering is yung array itself. So yeah, try to cut something in half at each point in time. And that should give you a solution that runs fairly fast. Okay, so that's for the searching problem. Alright, let's look at this next one. So here, what do we have? We have a sequence of integers, and you want a contiguous subsequence with the largest sum. By contiguous, what that basically means is consecutive. So here, you want a consecutive subsequence or a subarray that has the maximum sum. So here in this case, this 1 and 10, this is a subarray. This 10, 20, and 31, this is also a subarray. And this 20, 31, and 35, this is also a subarray. So how do we get the subarray that has the maximum sum? So here's an example. Note that this sequence can contain negative integers. So the answer is not necessarily yung entire list or sequence. If all of the elements were non-negative, then of course the answer would just be the entire sequence. So if there are negative elements, there's a chance that yung negative elements offset yung sum, which is why it's a bit more complicated if your sequence can contain negative integers. So for this example here, I believe the subarray here is this one. So this is 5 minus 4, 1 plus 2, 3, minus 1, 2, plus 4, 6. So this is the subarray with the maximum sum. Okay, so how do we do this? Well, as we went over, I think 2 lectures ago, if you have a problem, the first thing that you should try to do is brute force. So you want the subarray with the maximum sum. So you literally get the subarray with the maximum sum. So here you're enumerating all of the subarrays, then you're getting the maximum out of all of their sums. Simple as that. This goes through all of the possible subarrays, and because of that, this is obviously going to work. So for subarray sum, you can just implement that like this. So here it's literally just getting the sum of all elements in this specified subarray. So nothing fancy here. Okay, so this works, of course, but as you'll see, this is going to be slow. So why is this slow? Well, if we think about what's happening here, the number of subarrays, let's say you have 1, 2, 3, yung subarrays nito are going to be 1, 1, 2, 1, 2, 3, then 2, 3, or let's start with 2, 2, 3, and finally 3. So for a sequence with 3 elements, there are 1, 2, 3, 4, 5, 6 subarrays. So in general, if there are n elements, there are n times n plus 1 over 2, which is O of n squared. This grows roughly the same way as a quadratic function. So if there are this many subarrays, and each subarray, we get its sum in O of n times, since a subarray can contain at most n elements. So getting the sum of a subarray can be done in O of n time. So O of n squared subarrays, where each subarray takes O of n time. If you multiply those two together, you're going to get O of n cubed. So O of n cubed, if we have defined f of n, and I return here return n cubed, if we do f of 10 raised to 3, this is already 10 raised to 9. So by our estimate of 100 million or 10 raised to 8 operations per second, this is going to take 10 seconds already. So for an input with 1000 elements, it would take around 10 seconds, which is pretty bad. So can we do better? Can we make the solution faster than O of n cubed? So let's try to see what we can do. So here, this is our current brute force implementation. Is there anything here that we can optimize? Well, the first thing that comes up is this one. Remember in one of the previous lectures, we went over how to get subarray sums quickly. And that is by doing prefix sums. So again, the basic idea is, let's say you have this sequence here. If you want, let's say, the sum of this subarray over here, what you can do is you get the sum of this prefix, then you subtract from that the sum of this prefix here. So any subarray can be represented as a difference of two prefixes. So that's the idea that we can use here. If we pre-compute the prefix sums, so let's say we compute in advance yung prefix sums, and we have a dedicated function using that pre-computed stuff, then what we can do here is, this is still going over all of the possible subarrays, but here, for each call to subarray sum, this is just a single access to this list over here, and same thing with this one. So it's just two list accesses as well as a subtraction. So each call to subarray sum now takes O of 1 time, and since there are O of n squared subarrays, the entire running time is now O of n squared. So this is now a lot better than O of n cubed. If we do, let's just do it directly here, 1000 squared, this is 1 million, and that's around 1 over 100 of a second. So this is now pretty good, but of course this is still n squared. So if we have something as big as 100,000, this is still not going to be good enough. This would take around 100 seconds. So can we do even better than this? And the answer is yes. Now let's see how we can do that. Okay, the way we can do that is actually the same core idea, Sano search. So how can we use Sano search in order to get the max subarray sum? So when it comes to Sano search or binary search, you think about dividing something in half. So let's try to, well, since we're working with a array, let's split that array into two parts, the left half and the right half. Suppose that we can get yung max subarray sum of each of these. Since these are strictly smaller than the original array, we can use recursion or wishful thinking in order to get yung max subarray sum of each of these parts over here. And in that case, if we consider all max subarray sums of this left half, as well as all max subarray sums of this right half, the ones that are left are, well, what are the subarrays that we miss if we split yung array like this? Well, we already have all of the subarrays that are strictly in the left half, and all of the subarrays that are strictly in the right half. So that means what's left is the ones that are a mix of the left and a mix of the right. More specifically, it's a suffix of a left plus a prefix of the right half. So what you actually want here is the max suffix sum, or the suffix with the maximum sum of the left half, and for the right half you want the prefix with the maximum sum. So this is actually pretty easy. So you already know how to get the prefix sums in O of n time, and to get the maximum out of that, you just literally, well, wrap that around the maximum function. So how do you get the suffix sums? Well, if you think about it, let's say you have 1, 2, 3, 4. Your prefix sums are going to be 1, 1 plus 2, 1 plus 2 plus 3, and 1 plus 2 plus 3 plus 4. While your suffix sums are just going to be 4, 4 plus 3, 4 plus 3 plus 2, 4 plus 3 plus 2 plus 1. So to get the suffix sums, what you can just do is, if you get this sequence over here and you reverse that sequence, what you're essentially doing here is you're getting the prefix sums of the reverse of the sequence. So you can actually use the prefix sums function in order to compute the suffix sums, just reverse the array that you're passing into the function. Okay, so all in all, what this means is that if you want the max subarray sum, all you have to do is do 2 recursive calls, which have half the size of the original array, and in order to include the ones that you missed, that also takes O of n. So what that's going to look like is something like this. So let me have a text file over here. You have an original sequence with n elements. So you have n elements over here, and to compute this, it's going to take, let's say yung time that it takes to compute the max subarray sum. Compute max subarray sum of a sequence with length n. So let's define a function for that. To compute the max subarray sum, what we did here is we made 2 recursive calls, each for a sequence with half the size. So something like this. So 2 recursive calls of half the size plus yung additional O of n part here, plus O of n. So if we keep doing this step, for this particular t of n over 2, if we do the same thing, we also do it recursively, this is going to split into, this is t of n over 4 plus t of n over 4, then this is going to have its own O of n, and this is roughly plus around n over 2, since the input here is n over 2. And here, for the t of n plus 2, I'll just put this a bit to the right. This is going to be t of n plus 4, t of n plus 4, or n over 4, plus roughly n over 2. So this is going to keep going and going until your input becomes small enough. So what is happening in all of this? So this is eventually going to reach the point where it only takes O of 1 to compute. If you have a small enough sequence, getting the max subarray sum is only going to take around O of 1 for that sequence. So how do we actually, well, measure all of this? So what we really want here is we want to figure out what happens at the bottom over here. So all of this is eventually going to go all the way down into this last level, which is a lot of O of 1s plus all of the extra stuff that we went over from the extra step of getting the max prefix sums and max suffix sums. So the idea here is all of these O of 1s, each of these will correspond to a single element of t of n. So all of the O of 1s, this will sum up to roughly O of n. You can think of it as each O of 1 is corresponding to each element of the original sequence. And what's left now is counting all of the extra stuff. So in this level, we have around O of n of extra stuff. Here you have n over 2 plus n over 2. So that's also O of n. And actually, for each additional level over here, you're also going to get around O of n's worth of extra stuff. So O of n here. So same thing here. So the question is, how many of these O of n's are you going to have? So how many O of n's do you have here? If you think about it, what's happening at each level here is you're dividing n by 2. So from n, you go to n over 2, to n over 4, all the way down to the bottom level here. So this should look familiar, hopefully. The number of ways that you can divide 2 from n is going to be log of n, or log 2 of n. So that means you have log 2 of n of this extra stuff over here. So all in all, this extra stuff will give you O of n times log 2 of n. So if you add this and this, you're ultimately going to get O of n log n as the final running time of this entire thing over here. So in words, this is what it looks like. So here, what that means is, since there are, again, around log of 2n layers, what that means is the total amount of work that you do is going to be O of n times log 2 of n, which is roughly O of n times log 2 of n. Again, when it comes to big O notation, we usually ignore all of the constant factors over here. So yeah, O of n log n. So actually, when it comes to log n, we can just write it without the base. And the explanation for that is to yung log 2 of n and log n without any base. This is usually yung natural logarithm. This is just a constant factor difference. So again, for big O notation, we don't care about constant factors. So we can also write this as n log n. So if we have n squared and n log n, so let's go back here. So from mass, import log 2. So let's say we have n is equal to 10 raised to 5. If we compare n squared and n times log 2 of n, you'll see that n times log 2 of n is a lot smaller and a lot more reasonable than n squared. So this is more prominent for bigger n. So yeah, n log 2 of n is a very nice time complexity to have. So okay, this is how we do yung max subarray sum problem. Again, it's kind of like Sano search. So we're dividing yung subarray into two. Then based on the answers of the left half and the right half, we combine those as well as the extra stuff that we need to do. So that's max subarray sum. This idea where we have, let me go back here, where you have some input and you split that into several smaller instances. This is what we call divide and conquer. So you divide your input into several smaller parts. Then once you solve each of those smaller parts, usually using recursion or wishful thinking, you combine those smaller parts. That's the conquer part. And by combining those results, you can get your answer to the original problem. So this is divide and conquer. Okay,